Hi, Jamin.
Hello,
Hi.
am I audible? Yeah.
Yeah, you're audible. Yes.
Uh, just a moment. Do I need to enable the camera?
No, no, you don't need to if you don't want to.
It's fine. Hi.
Hi. So you're planning to attend this course? I mean, take the exam and
Yeah,
everything.
actually, yeah.
Okay.
So I already, I was just looking at the video, like still I'm yet to go with the second part of the week two.
Hmm.
Uh,
Yeah, so
because
if you have any questions, you can ask me.
Burnett and all, I have seen their
Yeah.
lectures. So
Even from week one, if you have any questions, and yeah, if you even in the week one lectures, if you have any questions from
so
that,
week
yeah.
one, so actually I was solving the assignment, and if you
Hmm.
can give me some hint, probably.
Okay.
Just a moment.
Yeah, sure. So week one assignment submission deadline is still not over yet, is it?
10th of August, I think.
Oh, okay. So yeah.
10th of August, yeah.
I think 10th of August is for week two as well. Is it?
Yeah, yeah.
Yeah, okay.
For both of the assignments,
Yeah,
yes.
yeah. So I was planning to discuss week one solutions today, but then I saw that the deadline is next week. So
Next week,
yeah.
yeah. But yeah, so first, second, third, fourth, fifth, sixth, seventh, eighth. So I don't know why, but it seems easy one, but eighth one was kind of tricky in a sense. I don't know.
So what is question eight? Okay.
It says that the sum of random variable, probability of sum of random variable greater than or equal to 10 raised to 6 is lower bounded by 3 by 4, but mark, and it says that using
Oh, right,
Markov,
right. Yeah, this question is a little bit yeah, it can be confusing. So uh,
because Markov give the upper bound, and
yeah.
the lower bound is given with the t in probability. So I don't know what I have done something. So I have used the Chebyshev inequality rather than Markov one.
Okay.
And Chebyshev, if I didn't write it properly, but I didn't get exactly. Like I just throw it out the answer, like this answer, but I
Hmm.
didn't get because Markov
Yeah.
is
So
like
okay. So let me just
8.
try to see. So the question is something like you have what? So can you see the screen? Can you see what I'm writing?
No.
Did you? Okay. So I just wrote x. So x1, x2. Can you see what?
Yeah, now I am able to see.
Okay. So and these are given to be exponential random variables, right, or something? Yeah. Um, okay.
Yes.
And you are interested in this probability that xi sum of xi is um, what is the question?
Sum of xi uh, greater than 10 is to 6 is lower bound by 3 by 4.
Okay. So I equals 1 to n, and you want to find a lower bound on n such that this happens, right?
Yeah.
Okay. So yeah, okay, so these are like positive exponential random variables. So as you have more and more random variables, the probability that it exceeds 10 to the power 6 will increase, keep on increasing, right? If you have more and more n's. So for sufficiently large n, what will happen is that the probability, so sufficiently large, and the probability that this sum is greater than 10 power 6 would be large, 3 by 4, right? And you want to find not the exact n, but some a lower bound on n.
Lower bound of n.
Yeah, so 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 basically we want some, say, n naught, okay, such that yeah, so basically suppose n star, okay, so suppose n star is the minimum n, such that this happens, right? The probability that I equals 1 to n 3 by 4. Okay, and so if it happens for n star, it will happen for all the n star, n bigger than n star as well. So
Yeah.
yeah, because these are positive random variables. Okay, so and you want to find a lower bound on n. So a lower bound on n star. Okay, so that n star must be at least this. So some lower bounds are very trivial. So for instance, n star has to be like greater than 0, greater than 1, right?
Hmm.
So those are also lower bounds, valid lower bounds. But yeah, we want something strong. So so if this is your number line, this is your n star. Okay, so yeah, you would want some. Okay, this is 1, suppose, and you want some lower bound on n, that n star must be greater than something. So okay, so now what will Markov inequality give you? Markov inequality will give you that I equals 1 to n xi is less than equal to something, right? It would be less than equal to expectation of. So these are exponential random variables with mean 1. So it would be just like n by 10 power 6,
Hmm.
right?
Yeah.
Okay, so right. So this probability. So okay, so let's call this probability some function f of n.
Hmm.
Okay, so what is f of n? F of n is what is probability that summation of xi, where I equals 1 to n, is greater than equal to 10 power 6, right? So this is f of n. Um, yeah, we know that f of n is less than equal to n by 10 power 6, right? And we want a minimum n such that f of n is greater than 3 by 4. So now if now you can try to see how to get a lower bound from this. Uh, right, that you want fn to be greater than equal to 3 by 4, and you have that fn is less than equal to 10 by 6. So if you combine these, right, so I mean that should give you some idea of how to uh, what is the, so this will tell you you'll need at least some n to get to 3 by 4 basically. Okay, so okay, so again you have some function which is increasing with n, first of all, and we know from Markov, so this is from Markov, that fn is less than equal to n by 10 power 6, and we are interested in minimum n such that fn star fn is at least 3 by 4. So now, right, okay, so okay, if I tell more, I think that would be the entire solution, but yeah, I think this is something uh, right. uh, okay, so suppose, okay, so one more hint, or one more way to think about it is, suppose like, okay, suppose this is some number line and some, okay, suppose 3 by 4 is here. Okay, and suppose you're hopping, with some step size, okay, on this number line. The question is what is the minimum number of hops you need to cross this 3 by 4? Uh, Okay, and so now I give you an upper bound on what is the size of this hop, like how much you are hopping. I'm giving you an upper bound. So I'm saying that you don't know exactly this length, right? Okay, so let's say, let's not make it exact. So suppose this is 10. You want to cross 10. Okay, and this is like hop size. So how many hops you need to go from 0 to 10? And suppose this hop size is very difficult to compute. So what you would do, so one way to get a lower bound on how many hops you need is say that suppose you can find out by somehow by some simple calculation that hop size is less than equal to 5. Okay, suppose you know this. So so then you can say something, right? So you need at least some hops to reach 10. You need at least 2 hops, right? Because hop size is less than equal to 5. So you'll need to hop at least 2 times to reach 10. So at least 2 hops.
No, it's at max 2 hop, right?
No, no,
Suppose
so
if hop size is less than equal to 5,
to 5.
then you will need 10 steps. So at max you need, sorry, at minimum we need
At minimum. So
minimum, sorry,
at
sorry.
least 2 hops.
Minimum you need two
Yeah, yeah.
hops.
So you see how this thing is working. You need an upper bound on hop size to get a lower bound on number of hops, right?
Right, right.
So that is how this is like Markov will give you an upper bound, and basically Markov will give you that the hop size is upper bound on hop size. So what is the minimum number of hops you need, right?
No, yeah, I will get, yeah, yeah, yeah.
Yeah, yeah. So yeah, so this
Then,
is a little bit confusing that yeah, I mean you need an upper bound to prove a lower bound, right? So
yeah, yeah, yeah.
yeah,
Understood, understood.
yeah.
Yeah.
Okay. Yeah, so this is so any other thing you wanted to ask from the assignment
Um, oh, I started the second
or
part.
from the lectures as well. If you
Mm,
or if you or maybe I can just yeah, I have just some questions which I can just try to solve and yeah, one or
yeah,
two
yeah, yeah.
questions and some discussion. So yeah, so these are like just to make you comfortable with inequalities and random variables and things like that. So okay, so
Actually,
this
sorry
hmm,
to interrupt you. Like
yeah.
the first lecture I missed, the first discussion session. So can you give me your intro? Or maybe I
Oh,
missed it.
right. Sorry. Yeah. So yeah, I'm Aditya Vikram Singh. So I'm one of the TAs for this course, and I'm a PhD student at IISc. So I'm working with Professor Himanshu Tyagi, who is a co-instructor for this course. Yeah,
So you are from electrical department,
ECE department.
ECD department.
Yeah. So yeah, yeah. So last time, yeah, we had a discussion last time. So last time again was an hour-long session, and I was solving some problem for the first half an hour, and then someone joined half an hour later. So then we had a discussion on yeah things. So
Mm-hmm.
so nothing much happened in the first session.
Mm-hmm.
Uh, yeah. So so, yeah, so could you introduce yourself? Like what
So yeah, so my name is Jamie, as
hmm,
you probably can see on the screen, and I'm currently studying in University of Minnesota in Twin Cities,
okay.
USA. So if you
Hmm.
have heard of it,
Yeah, yeah, I've heard of it. Yeah.
so yeah, I'm also a PhD student actually.
Okay.
Yeah,
So in which department?
electrical department only.
Okay, okay.
Yeah, so it's the first year student, so I need to learn some concentration bound and of course application in my research area. So
Yeah, yeah.
that's
These bounds are like very useful in every.
very useful.
Yeah.
Yeah, when the random variable is very complex and
Mm-hmm.
some kind of
Yeah,
intelligent. So yeah,
yeah.
so then I joined this course this time.
Okay, okay. Yeah, it's good. Okay, so yeah, so okay, let me just. So here we have like two random variables x comma y defined on a common probability space, right? So there is a probability space which is like a sample space, uh, right? And you know this probability space is defined by a triplet. You have a sample space, and this is like set of all the events, and then you have a probability measure on, right? So and now x would be some from sample space to real number, y is again some random variable from sample space to real numbers, and these are defined on the same sample space. Yeah, on the common probability space. So the question is which of the following are true, and it's not given that x and y are independent, they can be correlated. So for instance, x could be exactly equal to y all the time, right? Or x and y could be independent. So yeah, things like that can. So the question is, right, so what do we do here? So we want to, so throughout this course we'll see this function, right? This is the moment generating function.
Cumulant.
Yeah, this is the cumulative, sorry, log of moment generating function. So uh, yeah, okay. So now we know that, okay, so this is just expectation of x by 2 to expectation of into y by 2. And if these are independent, then these can be decoupled, right? So we can write it as x by 2, again expectation of y by 2, right? So this can be done, and then yeah, since there is a log outside, this becomes a summation. So for instance, b is true. Okay,
B is true.
yeah, but this required independence of random variables x and y. And then there are these other options which, okay, so now, so again you have two random variables here, e power x by 2 and e power y by 2. And so one way of decoupling them is using independence, which is a good decoupling. Another way of decoupling is like you can use something like a Cauchy-Schwarz inequality, right? So Cauchy-Schwarz is like expectation of x y, right? Or yeah, is less than equal to, right, expectation of x square, expectation of y square. So these are true for any random variables, and this is why this inequality is so useful, that you don't need independence or anything, right? You can just, so if you use Cauchy-Schwarz, so this is independence.
Sorry to interrupt.
Hmm.
This is also recording, and I will get it later, or
Yeah, so
this
this
is
session,
also part
yeah,
of the recording.
so this, I think the meeting is not being recorded, but I'm recording the everything. So I mean, we'll upload it on YouTube.
Okay, okay.
Yeah. Um, okay. So now, right. So if you use Cauchy-Schwarz here, so the square of e power x by 2 would just be e power x, right? So it would be expectation of e power x, but we get a square root. And again, expectation of e power y, we get a square root, right? Log of this. So this gives like half log expectation of e power x plus half log expectation of e power y, right? So which is option C.
Yeah.
So the thing is, yeah, you can use Cauchy-Schwarz to again decouple these things, and option D is also correct, right? Because the C holds for all x comma y. So even if they are independent, right, that again it will hold. So D is also correct. Um, that this holds. You can apply Cauchy-Schwarz even if they are independent. So there's no problem there. Okay, is it okay?
Yeah, yeah,
Yeah,
it's
okay.
okay.
So now, yeah, so again, so this is, let x be a non-negative random variable. So x is greater than equal to 0 all the time. And you have that expectation of x is greater than equal to 1. And now you want to comment something about expectation of x log x. Okay, whether it's greater than 0 equal to 0, or whether, can you say anything? So uh, okay, it's not obvious that it's greater than equal to 0 all the time, because log x could be negative even for positive x, right?
Yeah.
So we just have that expectation of x is more than 1, but x could be like something less than 1 as well. So,
Mm.
and some mass could be less than 1, some mass could be more than 1. So yeah, we don't know what will happen because of this log of x. So again, I think from week 3 or week 4 onwards, you'll see this function a lot, expectation of x log x, and this will, yeah, but so we want to comment something on it. Okay, so now, so one way is like, what can we say about this? I mean, this is easy to evaluate, right? If we could take expectation inside, if we, right? Because this would be expectation of x is greater than equal to 1. And again, since expectation of x greater, this log of expectation of x would be greater than equal to 0,
Mm-hmm.
right? So this thing is greater than equal to 0. And now the question is, how are these two quantities related, right?
Mm-hmm.
And so here we apply something called Jensen's inequality.
Yeah, yeah.
Yeah, so Jensen's inequality, because so fx, if you take fx as x ln x for x greater than equal to 0, um, yeah, so if we plot this function, so because of x, okay, so x ln x is not defined, log x is not defined at x equals to 0, but we can take limits and things. So if you take
Yeah, the
limit,
probability can be zero and yeah.
yeah, so it would be like 0 here, and then at x equals 1, uh, again fx would be 0 because of ln x, and then it, yeah, and since log x is negative here, it would be something like, this function. So x ln x, and um, right, in the limit it would almost look linear because you have x and log x is like small compared to x, so it will be,
Mm-hmm.
yeah. um, yeah, so basically this is a convex function, and other, I mean, you can also verify by taking like double derivative. So if a double derivative is always positive greater than equal to 0, then the function is convex, so for all x.
Mm-hmm.
So this is a convex function basically, and convex functions have this property that if you take expectation of f of x, and then versus f of expectation of x, right? So it turns out that expectation of f of x would be bigger than x, right? So uh, yeah, I discussed Jensen's inequality the with the with the one student who joined last time. So
Mm-hmm.
yeah, so it's basically that, right? I mean, why, I'm just trying to tell you why this inequality is true. And it's like, suppose you have a convex function like this. Okay. Um, okay, no, let me do it. So you have a convex function, and your random variables are, suppose, like, right? So your random variable is x, which takes x1 with probability, say p1, x2 with probability p2, and x3 with probability p3. Okay, so this is your random variable would be on the x-axis, and it takes only 3 values. And we are interested in f of x, where f of x is this curve above, right? So we are interested in this, right? And now, because this is a convex function, what happens is, you have these line segments. All these line segments would lie above the function, right? This is basically the definition of convexity, that
Hmm.
take any 2 point, the
Yeah.
line segment will lie above it, right?
Maybe, maybe isn't it like we can just
Yeah, the definition of convexity is like, take any,
definition of convexity and then apply the expectation for in place of variables we apply the expectation
yeah,
of
yeah,
x.
yeah, yeah, that's true. So in the definition of convexity, you have definition for 2 points, right? Take any x1 comma x2, right? And then, so, but yeah, geometrically this is what is happening, that now
Mm-hmm.
if you see, this triangle is above the function, right? So now if you take expectation of fx, uh, uh, so if you look at like expectation of fx comma expectation of x, sorry, expectation of x, so expectation of x would lie somewhere on the x-axis, right? Between x1, x2, x3, somewhere here.
Mm-hmm.
And expectation of f of x, the coordinate would lie inside. So basically, this coordinate would lie inside this triangle, is what I'm saying. Basically, you're taking centroid of this, or centroid in a vague sense, right? So suppose it lies here. So right. So which means that expectation of x is here, and expectation of f of x is here, right? and f of fx expectation of x is here, right? So so this is basically Jensen's inequality. So the thing is that this polygon or whatever is will lie above the function, and so your expectation of f of x would be higher than uh, f of expectation of x, right? So this is Jensen's inequality, and it's used a lot. And yeah, I think we have recordings of the season, not season one, week one live session. So there I've discussed like how you can derive AMGM or Young's inequality or Holder's inequality, everything using this Jensen's inequality only. So starting from Jensen's inequality, you can derive all these basic inequalities. If you want, you can have a look whenever it's open. Yeah, so I think, yeah, so these are the only two problems I have because I thought I'll discuss solutions, but again, it turns out that the deadline is next week.
Mm,
Okay, so so have you heard of this term radon Nicodim?
mm,
No, you haven't. Okay, so yeah, this is a very complicated name for a simple thing. So in I think in lecture week two, lecture one, there is this notion of exponential tilting, which is used in proof of Hövding's lemma,
yeah.
right? And the main thing there was that you had something like, so x is some random variable, right? And p is say
Mm,
distribution of x, and so you had this thing that you wanted to compute with respect to p. Uh, yeah, you have this quantity, suppose,
mm,
right? And the question is, it was basically, yeah, it was again uh, x e power lambda x. You had some quantity like this in the proof, uh, and you wanted to make sense of this quantity. Okay, in the lecture, what x had this property that x lies in a comma b, suppose.
yeah.
So then variance of x is less than b minus a square by 4. Okay, this is always true no matter what the distribution of x is.
Mm,
You take any distribution of x, variance of x. So for instance, if x lies in 0 comma 1, your variance would always be less than 1 by 4, no matter what you like, no matter what the distribution of x is. So that was something. And now we had this quantity which we want to make sense of. So what the trick was that you can write this as expectation x square. Okay, first of all, you can just take this inside because the denominator is just a constant. It's an expectation of it's a moment at lambda, so this is a constant. And now you can define a new probability distribution. Okay, define a new probability distribution q. Okay, so what is, and how you define this probability distribution is as follows, that q of x by p of x would be e power lambda x into some constant alpha. Okay, so right, so you can always do this kind of thing. So suppose, okay, so let's take an example. Suppose x is a random variable which takes a1 with probability p1 and a2 with probability p2. Okay, so p is a distribution, p is basically p1 comma p2, the distribution of x. Now I'm saying define a new distribution q, and what would q be? Q would be uh, p1 say e power lambda a1, p2 e power lambda a2. Okay, but again, this might not be a distribution because this might not sum to 1 basically. And so we divide by this normalizing constant, which is like p1 e power lambda a1 plus p2 e power lambda a2. And again, this again p1 e power lambda a1 plus p2 e power lambda a2. Okay, so now this is a valid distribution. No matter, we don't care if a1 is positive or negative, a2 is positive or negative, because we have e power lambda a1, which will always be positive, right? So we have two positive numbers and e power lambda a1, e power lambda a2, and we multiplied by p1 and p2, and right. So we have a new distribution. So if you just see, what will happen is q a1 by p a1 basically is e power lambda a1 by, right, by expectation of e power lambda x, which is like p1 a, right, and q a2 by p e2 is e power lambda a2 by this constant, right? And okay, so we call this new distribution, q is called the exponentially tilted version of p. Okay, and this ratio qx by px, this is called a Radon-Nikodym derivative. Okay, so the name is like Radon-Nikodym derivative of q with respect to p. So basically what it means is that you had some underlying p, you defined a new distribution q by defining this some function of x, which is a positive function e power lambda x, and then just multiplying p with that positive number, and then dividing by some normalizing constant so that it actually is a distribution. Okay, and in general, so this was for discrete random variables. You can also have it for like continuous random variables. There qx and px would be pdfs, and yeah, so the notation for this is like dqx by dpx. Okay, this is just a notation, doesn't mean anything. Sorry, it's not d, it's dq by dp of x, right? So this is just a notation which basically means this ratio. And so once you have this, so now you can look at this quantity here. It is just with respect to this new distribution. It's a second moment with respect to this new distribution q. Okay, and again, if you do the similar thing here, this is just, this would again be like x square. So totally what we have is that you have like minus e q x the whole square. Yeah, so this is like variance of x when the distribution is q.
And the distribution,
Yeah,
yeah. So,
so and now we know that variance of x is less than equal to b minus a square by 4, no matter what the distribution is, when x is limited to a comma b. So now you can use this upper bound to upper bound this weird, this strange looking quantity, right? This looked very complicated,
yeah, yeah.
but then you can, using this Radon-Nikodym, that okay, you can see it as a variance with respect to some other distribution. Okay, and so this leads to this thing. So again, this Radon-Nikodym derivative will be used a lot in from I think week 3 or week 4 onward. So yeah, we'll have more questions on this.
One more question.
Hmm.
Are there any assumptions or kind of to apply the radon Nicolin, like it's bounded support or something?
Yeah, so you basically need that once you multiply it. So if, okay, so you have a distribution p, suppose. Uh,
I mean, what's the is there any limitation you see, or there aren't
no, so
any?
basically you should be able to define a thing. So it should be first of all integrable, the function you are using. So for example, we used e power lambda x by expectation of e power lambda x to define, and this was like Radon-Nikodym derivative, right? So this quantity should be, first of all, the moment should exist, not moment, the expectation should exist, right?
MGF
So
basically.
yeah, mgf, or in general, if you have like any function, say h of x, you can define your Radon-Nikodym derivative as dq by dp of x as h of x. Wait, I think some, um, hi PMRF support.
Support.
Yeah, I think this is just to see that things are going smoothly. So uh, yeah, so we have this, suppose h is some any function. Okay, we define this new a new distribution q of x, and how that q of x is defined is, suppose p of x is density p of x, you just take p of x multiplied with h of x, that would be q of x. Okay, but this may not be like the integral should be 1, right? Q of x dx. So basically you need to divide it by expectation of p h of x, right? So basically if you have any function and you, right, and you have an underlying distribution p, and you want to define a new distribution using this hx by multiplying it with p, it's the expectation of hx with respect to p should exist, and of course hx should be positive. So these are the only two conditions. Okay, and
Okay.
so and then you basically just, this is called tilting, you tilt the distribution p to get a new distribution q, and what you will have is that expectation with respect to p of any function, say of a random variable, say y, would just be expectation with respect to q, right? Suppose like y of x is something, y of into h of x. Okay, so this is what it allows you to do that. Yeah, sorry, expectation of q, it should be like this.
Otherwise,
Yeah. Okay, so yeah, so if you have some complicated looking quantity like this, you can see it as like expectation with respect to some other distribution, and and you can use properties of like any probability distributions and things. Okay, so this is radon Nicodemus derivative or exponential tilting. Yeah, there are many names of this. Exponential tilting because you're multiplying with e power lambda x, but in general you can have any positive function which is integrable. Okay, and now then we had this Hovding versus Bernstein, right? Or Bernstein, I don't know. So Bernstein in this lecture. So basically, right? So the thing is that Hovding just uses uh, worst case bounds on x. So if x is in a comma b, right? Hovding basically assumes that the variance would be b minus a square by 4, which is the maximum variance possible, because that was used in Hovding's lemma. That this is the maximum variance possible. Okay, and Bernstein, what it does is it uses actual variance of x. So sometimes what may happen is that the actual variance may be very small with compared to the worst case variance. So if you have, okay, so for instance, consider this thing. You have n balls, okay, and to each ball you assign one of the n bins uniformly at random. Okay, so let's say C1. So bin would be like, since ball and bin both start with B, I'll call this bin container. So C1 is a container in which ball 1 is assigned. Okay. C2 is a container in which ball 2 is assigned, and Cn is a container in which ball n is assigned. So what we have is that C1 is a uniform distribution, uniform over 1 to n. Okay, because like there are n bins. We label these bins 1 to n, and then we have like balls here 1 to n. And so ball 1 would be, take uniformly any bin from 1 to n, just assign it there. Similarly, ball 2, so this is C2, container for ball 2 is like again uniform distribution 1 to n. Container for ball n is again uniform 1 to n. Okay, so you have these n, and these are all independent, right? All independent. So suppose, so you have done this allocation, you have n balls, and then you assign like one of them randomly to one of the bins. And so now the question is, like, suppose you were interested in C1. So, sorry, say Z is number of balls in bin 1. Okay, so which means you want to see that you had like n random variables, how many of them are 1? Okay. Uh, okay, so C1 is like where is ball 1 assigned, where is ball 2 assigned, where is ball n assigned, and you want to see how many balls are assigned to bin 1. So you have n random variables, how many are? Okay, so you can tell that, okay, so Z is what? It is basically, it would be what? Bernoulli of 1 by n. Okay, so you just want to see whether whether okay, whether C1 is 1 or not, right? Whether C2 is 1 or not, right? So okay, so basically Z is not this. Z is like I. So we'll write this: I equals 1 to n, indicator Ci is 1, right? So if Ci is 1, it will add 1 to this Z. Otherwise, no, right? If Ci is not 1, this will be this is the indicator random variable. Okay, and each of these random variables is Bernoulli 1 by n, right? Because C1 is equal to 1 with probability 1 by n, right? And C1 is not equal to 1, which we don't care about. It could be either 2 or something or anything, but with probability 1 minus 1 by n. We are only interested in container 1. Okay, and so we want to make some high probability statement like what. So okay, one thing is, what is expectation of Z? Expectation of Z would be, you have n independent Bernoulli, so it would just be n into 1 by n equals 1, which makes sense. You have n balls and n bins, and uniformly at random, and so yeah, in expectation you have 1. And so, but what this course is about is you want to make high probability statements. So right, if you in general, if you have like algorithm or you design some system, you don't want it to be true only in expectation. You want to make some stronger statement, which is where concentration inequalities are useful. That okay, expectation of Z, okay, so in expectation it's 1, but yeah, what is a high probability statement? So what Hövding gives you is that, so suppose you want to make this probability statement with probability delta, right? So basically, how many balls in container 1, in bin 1, right? How many balls in bin 1? So this is a random variable, and with probability at least 1 minus delta. So you want to give an answer so that you are sure with at least 1 minus delta that there are these many balls in bin 1 with probability at least something. Okay, and so Hövding just gives you that probability, and this is exactly what is done in the lecture. So Sn is basically Z. So it's basically Z. Z is the Z minus expectation of Z is less than equal to root n by 2 log 1 by delta. Okay, this probability is at least 1 minus delta. So this is Hövding's. Okay, and this use the fact that Z is, so each component of Z, which is like this indicator function, all these lie in 0 comma 1, and so in worst case it could be something like root n. Like you have n random variables, uh, each in 0 comma 1, right? And you have this Bernoulli, these are Bernoulli random variables, so standard deviation would be like root n in general. So so this is what Hövding gives you. But if you just use the other thing, Bernstein, so that uses the fact that even though all the random variables, this indicator, they lie in 0 comma 1, its variance is very small, because mean is what? Mean is 1 by n, because Bernoulli 1 by n, and variance is just 1 by n into 1 minus 1 by n, which is very small, right? It's basically just, it's less than equal to 1 by n. So your mean is 1 by n and variance is also 1 by n, right? And Hövding was assuming that your variance would be like 1 by 4. So this gives a huge improvement. If you use Bernstein now, and again, this is in the lecture, you have like log 1 by delta plus say 4 root log 1 by delta. Uh, yeah, this is greater than equal to with probability 1 minus delta, right? So basically what Bernstein's allows you to say is that the probability of z is less, expectation of z is just 1. So 1 plus log 1 by delta plus some 4 root log 1 by delta, right? This is greater than equal to 1 minus delta. So, and whereas Hovding gave you 1 plus root n by 2 log 1 by delta, right? And there's a huge difference here because like if you want to be confident with say 10 power or yeah e power minus 6, then what would this would be just be 6, this would be root 6 here, right? Whereas if you use Hovding, you'll have like a factor of n as well,
Mm-hmm.
right? So so in basically if you're designing a system and you want to compute like with high probability what will be the load on that system, okay?
Mm-hmm.
So so Hovding gives you a very conservative estimate that load would be like order root n. But Bernstein tells you that no, it's like order some constant. Once you fix your confidence interval, it's basically 1 plus say 6 plus root 6, right? Something like that. So you can be more aggressive in your system design if you use these stronger inequalities. So this is what is basically the difference between Hovding and Bernstein. That Bernstein lets you use the actual variance of x, and Hovding assumes that okay, if x is in between a and b, I'll use the worst case variance, right? So suppose all these Bernoulli random variables like were probability half or Bernoulli half. In that case, Hovding would be okay. It gives you something like root n, or, but it's only when variance is very small. Its variance is like 1 by n here. And in those cases, like Bernstein, uh, yeah, helps you a lot. Okay, and yeah, so you have not seen these lectures, so I'm not sure. But again, um, have you heard of these? You must have heard of what is conditional expectation, right? Conditional expectation is yeah. Um, Martingales.
Yeah, I have
You,
checked, like I have seen that part of the lectures.
oh,
Half
okay,
of the
okay.
part, half of the second lecture I have already almost completed.
Yeah, yeah, okay. So,
I completed some articles as well.
mm, yeah,
Like the
so,
difference, conditional difference will be the like that kind of thing.
yeah, yeah. So those things. So, yeah, okay. So martingales are again, yeah, very, very useful. Okay, so there is one thing for martingales, which I should clarify. So suppose you have these random variables x1, x2, x3, and so on. Suppose this forms a martingale. Okay, so martingale is like another formalism. So for instance, you want to analyze these random variables. The simplest assumption is assume that they are all independent, right?
Mm-hmm.
X1, X2. And martingale assumes that, okay, there is some other condition and which also makes calculations very tractable. And that condition is that expectation of say xn plus 1 given x1 to xn. Okay, this is xn, right? So this looks like Markovian property, but this is not Markov chain. This is yeah something else. It's like yeah once like 1 to n, once you have observed 1 to n, suppose what is the expectation of the n plus 1th random variable?
Yeah, and
So,
Marco is kind of on the right side. It will be expectation of xn, right? I think.
yeah, so Markov would be the Markov is in terms of probability that xn plus 1 lies in some set
Mm-hmm.
given x1 to xn. This will only depend on like this with some function of xn basically,
Mm-hmm. Okay.
right? So
I get it.
that is some Markovian property that
Yeah,
given the entire history, only the last point is
yeah, yeah.
useful. If right, and martingale is like you. So what you have observed. So x1 to xn is like you can think of what you have observed, which is how it's used in practice. And xn plus 1 is something you haven't yet observed,
Mm-hmm.
right? So for instance, like weather condition, right? What is the temperature you have observed, like n temperatures? What would be the temperature on n plus 1th day? And what this is saying is, okay, n plus 1th related temperature would be random, but its expectation would be whatever the previous day's temperature was,
Mm-hmm.
right? Which is right again. So all these the temperatures are not independent in you, right?
Yeah, yeah.
The temperature is like x n plus 1 would obviously depend on xn, and it also depends on like previous temperatures. But yeah, so what you can claim is like the on n plus 1th related temperature would be on average the same as what temperature it was on the previous day. And yeah, so this is what is martingale. Sub martingale is like, okay, it's sub martingale is the name and definition, they seem to like contradict each other. So like this has to be greater than equal to xn.
Yeah.
Okay, this is like sub martingale, that on average your temperature is increasing. So for example, like if you are going from April to May, in that period, the temperature on n plus 1th day, the expected temperature would be more than what the temperature is on the nth day, right? So this is called sub martingale. And now, okay, so now suppose you define a new random variable. So you have x1 to x, which is martingale. Suppose you define a new random variable y1, which is f of x1. Okay, y2 is f of x2, and so on. So the question is, what can we say about these y's?
Mm-hmm.
Suppose f is a convex function. Okay, so now, or f is, yeah, suppose convex. But what I want to tell, or what I want to clarify is, suppose you want to prove or check if y1, y2, and so on forms a martingale. Okay, so the condition you want to check is this: that expectation of y n plus 1 given x1 to xn, you want to see if it's equal to or greater than equal to or something submart, right? Is it greater than equal to y of n? Okay, so this is what I want to clarify, that the conditioning should be on x1 to xn.
Mm-hmm.
Okay, if you take a formal mathematics course on probability,
Mm-hmm.
uh, they have this underlying sigma algebra for, right, and things like that. But yeah, so when you take a function of these x's, so x1 to xn is what is forming the basic sigma algebra.
Mm-hmm.
So when you want to check this martingale condition on y's, you should check it with respect to this x1 to xn. Okay, you should, if you try to do this like yn plus 1 given y1 to yn, this is not what we want. Okay, so the martingale definition, yeah, so in engineering courses this is not like emphasized a lot, but in mathematics courses they say that martingale with respect to a filtration, they use this word filtration, which is like a collection of sigma algebra. So so in our case, basically what you have is that just focus on this underlying random variables. This is the basic information you have.
Mm-hmm.
Y1 to yn is just some functions of those information. Yeah, and so whenever you want to check the martingale condition, what you have observed till time n is, you have also observed x1 to xn, right? So basically the way to think about martingale is what you have observed till now. So you have observed y1 to yn, okay, but you have also observed x1 to xn, that is also happened. I mean, we assume that all the random variables till time n has been observed, and then you want to say, yeah, what is yn plus 1? So yeah, so for instance, there is a,
I think if you let what you can say, what maybe I can think of, if f is on two,
hmm.
then we can also
Yeah, yeah. So in that case, you're right. Yeah, F is like, or one to one basically.
one to one.
Yeah,
Yeah,
that there is a one to
vertically.
one relation between x and y's.
Yeah, yeah.
But yeah, but in martingale,
Yeah, in general, this is a
yeah,
very generic x1, but
yeah. So for instance, there is this theorem that if x1 forms a martingale, x1 x2, then f of x1, f of x2, and so on, this is martingale, will will form a sub martingale.
mm-hmm.
Okay. Yeah, and So we use this in this lecture where f of s is basically e power lambda x1, e power lambda x2, and so on. And we use something called Doops inequality or something. So there we use the fact that, yeah, this forms a submartingale. Okay, so submartingale is what? Submartingale is like a random process which is in general increasing, right? Because expectation of xn plus 1 given this is greater than equal to xn. So submartingale is like an increasing thing. So if xn1 martingale is like things stay more or less constant, right? And so if x1 and x2 are martingale and f is a convex function, then e power lambda x1. And the way to prove this is, when you prove this, you have to compute like e power lambda xn plus 1 given x1 to xn, right? Don't use like here e power lambda x1 to, I mean you can, but yeah. So that would be the way to show that this happens. So yeah, so basically instead of having like independent random variables, you can prove theorems for martingales as well, concentration inequalities. And yeah, so and concept and martingales are like very general, uh, like there are a lot of processes which can be which can be defined as a martingale. Yeah, and the last thing I want to just say is that there is something called Talleyrand's principle, which was discussed in first lecture, and I think even in this week's lecture, which is like you have independent random variables x1 to xn, right? And you can have any weird function of f of x1 to f of xn, right? The x1 to xn are independent, so that is okay. But we have f of x1 to xn, which can be, uh, so for instance, we have this question in I think homework 2, which is like, yeah, okay, I think in first lecture, Professor Aditya Gopalan, he discussed like many examples of what fx1 to xn could be. Right? He discussed some coupon collector problem that you are collecting coupons, and then how many chips you need to buy to collect all the coupons and things like that. Right? So, so how many chips you need to buy? That function is f, right? And it's much more complicated than a simple sum like x1 to xn by n, right? And in this week two's lecture, the pinnacle of week two's lecture was proving that suppose f satisfies BDP. BDP is like this bounded difference property. Okay, what it means is that f is a function. So if you have like f of x1 to xn, and if you look at f of x1 dash and leave all the others same, in this case, this difference should not be too high. So this difference should be, let's say you can bound this, that if you choose if you replace any one of the random variables xi, the function value cannot change by a lot.
This difference is bounded to
Yeah, the
C1.
difference is bounded by C1. So in this case, you have like concentration inequalities, like probability that f, or yeah, f of xn, which is like x1 to xn minus expectation. This would be, or this is greater than t, with probability less than e power t square by 2, say c1 square plus cn square. Where c1 square, c1 is like how it changes if you change that variable 1, cn is how much it changes if you change variable n, right? And so Talleyrand's principle is basically that if you have a function of random variables, and each random variable plays only a small part in changing f, and that is captured by this, that if you change one variable, it changes by at most c1, then you can prove strong concentration inequalities, basically. And I think throughout this course we'll see like many instances of basically McDiarmid, which is this is McDiarmid's inequality. This basically is one of the most useful instances of this principle, right? And week two's homework has a question where, yeah, so it's a bin packing problem. It's explained in week two's question, but yeah, so again, it's a very complicated function that you have n objects. How many bins you need to pack those n objects, where each bin has a certain capacity. So you have n objects and with certain sizes, and so how many suitcases you need to pack them and things like that. So the number of suitcases required is f, right? And the thing is that if you just replace one item, you'll the number of suitcases won't change by very much. If right, so from x1 to xn, if you just change say x1, you increase the size of x1 by a certain quantity, then the number of suitcases required to pack those items will not change by much. And so this number of suitcases required is a that function satisfy boundary difference principle, and so you can use McDiarmid's inequality to show strong concentration.
Mm-hmm.
Okay, and so yeah, so that is basically the most important. I think week two is like all the things you need in your research. If you just stop this NPTEL course, attending this course, week one and week two will get you through most of the things you need throughout your research. So from week three onwards, yeah, we'll see other things. We'll see like, so these are like black box results. You can use them if those functions satisfy this property. But from week three onwards, we focus more on like techniques. How can we derive for general random variables, which may be specific to your research? What are the techniques used to uh, yeah, to derive concentration? So and bound variances and all that. So yeah, that would be from week three onwards. But yeah, this is all I plan to discuss this week. I think next week we can discuss some homework solutions and yeah, things like that.
Sure, sure,
Yeah.
sure. I have one kind of general questions.
Hmm.
Uh, so all these, so till now at least, we have a upper bound on tail probability. Is
Hmm.
there any kind of suggestion you give to lower bound the tail probability,
Or to
or you
lower.
just need, because I think in my research I need some kind of that stops. Lower bound on tail probability.
Okay. Yeah. So lower bound is like okay the probability that the function exceeds this is at least this much, right? Something like that.
Yeah.
Yeah. Um, lower bounding tail probabilities. So
I'm just asking.
yeah, yeah. So of course you can do things there, but yeah. So there is this topic called anti-concentration. If you search Google, okay, just search that. So anti-concentration is like, yeah, there is this huge probability that you will not lie within some uh, bounded interval around the expectation. So there are some results there, but yeah, I'm not very sure, but yeah,
Yeah, no,
you
no. That much only I needed some
yeah, yeah. Just look at that
number
and
or something so that I
mhm.
can search on
Yeah, I think there are some lecture notes also available online. I'm not sure, but yeah, on purely on anti-concentration properties. Like,
Yeah.
yeah, what is the
And
probability?
one theorem I was looking at Berry-Essing, if you have heard of Berry-Essing theorem.
Oh, Berry-Essing is, I think it's just like you quantify central limit theorem, right?
Yeah, yeah.
Yeah,
It's a center kind of center limit theorem.
central limit theorem. So,
But
but won't Berry-Essing give you like, won't it give you an upper bound on tail probability?
both.
Or it gives,
It's give a upper and lower bound both.
but it's like,
It's generally speaking, it's a kind of absolute difference between CDF of random variable
hmm,
plus normal
hmm,
is bounded by some quantity. So
okay.
since it's a absolute value bounded by some quantity, we will give upper and lower bound both on the CDF.
Oh, in that sense, okay. Yeah.
So
No, so basic,
due to
but when we say tail probability, it's generally like tail on both the sides. So
yeah.
if you give an upper bound on tail on both the side, you will have that with high probability you are in this interval
Mm-hmm.
because you're saying that the probability that it's outside on the right side and outside on the left side is very small. So
Mm-hmm.
with high probability you'll stay within that interval. So that would again be a concentration inequality. Okay, because you're saying that you are around within that interval around that expectation, both right and left. So you have expectation of x, and then you have expectation of x plus some quantity, expectation of x minus some quantity, and you are within that interval with high probability. So that is concentration because your mass is getting concentrated there. Anti-concentration would be like you have
Yeah,
expected,
yeah. I
yeah,
understand.
that you will have a certain weight outside as well. So you will give you so anti-concentration would be that the probability that you are outside that interval is at least something, right? So yeah, so you just look at that anti-concentration. I think you'll find some good results there. Yeah,
Yeah, yeah. I will search for it.
yeah. Okay, so I think yeah, it's more than
Okay,
yeah,
yeah.
it's
It's
already full.
time is also up, and
Yeah,
I
yeah,
have to.
yeah. Okay, nice to meet you too. So yeah, let's meet next week then. If you have any questions, you can just join. Okay.
Sure.
Yeah, okay.
And
Hmm.
okay, yeah, sure. Thank you.
Yeah, okay, bye.
Have a good day. Yeah, bye.